Hello, people from the future. Welcome to Normalized Nerd. So today I'm gonna be talking about R squared and adjusted R squared. I will explain the concept and I will also give you the necessary intuitions behind this. Okay. So before starting, please subscribe to my channel and hit the bell icon if you haven't done already. I make videos about machine learning and data science regularly. So basically, R square is the measure of correlation between two variables, and in machine learning, we can use this R squared and the adjusted R square as an evaluation metric. So to understand the R square, let me give you an example of a simple linear regression. Here you can see that I have a fake data set. Along x-axis I have plotted the free time I have per month, and along y-axis I have plotted the number of videos I have made in that month. Okay. So these yellow points are actually my data set, and by looking at this data set you can say that okay, there is a positive correlation between these two variables, and if this is our independent variable and this is our dependent variable, so our model will predict this as output variable. All right, and this will be our feature. And say after doing the least square method, we have found this red line. All right, so how can we define a model for this red line? Well, we can write it something like that: y is equal to beta x. And how we will be able to find the beta? Well, we can just add a term something like epsilon, which basically refers to error term, and if we just change the sides, then it will become y minus beta x equal to epsilon. And if I just square the epsilon, we will have y minus beta x squared. And if we just use least square method, then we will be able to find this beta, that is the parameter of our model. And if you really want to dig deeper into the linear regression, then I actually have a video dedicated to linear regression. Please check that video. So this model corresponds to this red line. All right, so how can we determine how good or how bad our model is? Well, to do that we need to have some reference, right? And in R squared we take the average model as our reference. So what is an average model? Well, average model is actually a model which predicts the average of output variables for every value of x we feed in. Okay, so this is my x, and you can see that if you follow the green line, then no matter what x you feed to this model, it will produce only one value, and this value is actually the average of all the heights of yellow points. In other words, this is the average of all the number of videos. Okay, so now we have a reference line and we have our model. So now we are at a position where we can compare them and we can compute the effectiveness of our model. So to do that, R squared gives us the way, and R squared used a statistical measure called variance. Well, what is variance? So variance generally means how much spread out our values are around its mean. Okay, so if we just write the formula of variance, we can write it something like that. So variance of x, well, let me use some other variable because this x will cause you trouble. Okay, so let me just say variance of z is nothing but the sigma, obviously, over all the points. And here we have z I minus z bar. Well, ideally we have here a 1 upon n. I am just omitting it because this is not needed for our formula. So the formula of r square goes something like this: r square is equal to 1 minus variance around our predicted line. That is, I am writing it in red because this variance refers to the variance along this line. Okay, and in the denominator we have variance along our average line, that is the variance along this line. So what will be the formula for both of them? Well, that is actually pretty similar to that. And in the denominator you can see that we are calculating the variance around this average line, so obviously this will be same as this, so I can write it as sigma, and for your understanding I am writing here I is equal to 1 to n, and remember n is the total number of yellow points, and here we have yi, and in my videos I have told it many number of times that yi represents the ground truth, that is this original data points, and difference between that and our average, and you have guessed it right that this y bar is actually this value. Okay, so this was our denominator, and what will be in our numerator? Well, in our numerator we will have, well, I am omitting this I and n because of space problems. Okay, so sigma yi, our ground truths, and our predicted values. Okay, now ideally we calculate the variance over average, but here in the numerator we are calculating the variance around our predicted model. That's why I have replaced y bar with y hat. We know now what is the formula for r squared and why we use that. Alright, so let me give you some intuition about this r squared. Well, suppose somebody says you that r squared of your model is say zero point 0.8. So what we can infer from the statement? This statement tells you that our model captures or explains 80% of the variance in our dataset. And obviously, if you can explain a higher amount of variance through your model, then your model is a better model. That's why if your r square is close to 1, then you consider your model as a good model. And if it is closer to 0, then it is a bad model. So that was all for the r squared. Now comes the adjusted r squared. So the first thing you need to ask yourself, why we even need another matrix? We already have our r square. Why we can't be happy with it? Well, the thing is, suppose we have a model with n features and we now add a new feature, so the number of features become n plus 1. And now if we calculate the r square for our new model, it will always give a value greater than our previous model. So it is telling you that our new model is actually a better model than the previous one, but it may not be true because we can add as many features as we want to our model which have nothing to do with our output variable. So in that case it will only contribute to the overfitting, it will not learn anything. Okay, so this is a huge problem. Now to just give you an example, I am taking the same fake dataset as my example. Okay, so here suppose I am adding a new feature, that is the average temperature, average temperature of that month. Now obviously this average temperature has nothing to do with the number of videos I make on that month. So if I add this feature to our model, and the model will become, say it becomes beta 1 x1 and beta 2 x2 plus epsilon. Now suppose x1 represents this free time and x2 represents this average temperature. Okay, so our new model will produce r square value that is greater than our previous model, but this is in no way a better model. That's why we need a new matrix that will somehow tackle this problem. Now if you are really interested and want to know why our new model can never produce an r square less than our previous model, here's the intuition for you. Well, what we do in least square method, let me just write a few steps here. So we minimize our square error, and the square error is nothing but y minus y hat squared, right? And this y hat is actually our model, that is beta x, obviously. Now in the first case we have only one variable. Okay, so let me just write this function as minimize y minus beta x1. Okay, so this is the optimization equation for our first model with one feature. Now what happens in case of the second model? That is, we have two features here, so the equation becomes y minus beta 1 x1, oops, let me write it again, x1 and minus beta 2 x2. And by solving these optimization problems we find beta 1, and in this case beta 1 and beta 2 both. Okay, so what happens in the optimization? In the first case, say we find some value of beta 1. Okay, and now when we come to our second step, remember that x1 is a valid and useful feature, but x2 is not an useful feature. But our optimization technique will find the beta 2 anyway, right? In the worst case, it can assign beta 2 as 0. So what will happen in that case? In that case, our model will be same as our previous model, right? Because you are just putting beta 2 is equal to 0 here and the x2 has no effect. So our model becomes our previous model. What can happen in case 2? Well, in case 2, the model will find some value of beta 2, which basically means that our model has found some relation with x2 and y. In reality, we know that there is absolutely no relation, but we can even find pattern in randomness, right? So that's why our model has found some pattern from this randomness of x2 and take that correlation, no matter how small the correlation is, into account and gives a non-zero value of beta 2. Now obviously this slight correlation actually harms our model because it fails to generalize. The r square value will be greater than this previous one. Now what can happen in the worst case that I have mentioned? When beta is equal to 0, it will produce the same r square value. I have just shown you why the r square value of our new model can never ever be less than the r square value of our previous model. So now I am going to show you what is the new metric, that is what is adjusted r square. The formula is actually very simple and it is kind of an hack. So the formula goes like this: adjusted r square equals 1 minus 1 minus r square, this is the normal r square, times n minus 1 in the numerator, and in the denominator we have n minus m minus 1. So what is n? Well, n is the number of data points, okay, and m is the number of features. Now what we assume here is that the m features are independent, so this is also called as the number of independent features. That is, the features we are feeding to our model are all independent of each other. So this little change in formula has some beautiful effect. See that our r square is increasing in the second case, but at the same time the m is also increasing. So the denominator decreases and the r square increases. So these two opposite effects. So even after adding a new feature, if we don't see a significant increase in our r square, the adjusted r square will not increase. That's how we somehow tackle the problem of adding a new feature. So that was all for this video, guys. I will definitely post a video in the upcoming weeks where I will show you how you can actually compute this r square, adjusted r square, and some other metrics using our favorite library scikit-learn. So please stay tuned for that video. I will definitely link that video to the description of this video when I will upload that. If you have enjoyed this video, please like this video, share this video, and subscribe to Normalized Nerd. Thanks for watching.